All right, good afternoon, everyone. We still have 2 minutes before 2. So settle in, and if you can share this link with your colleagues and friends so they can join us, that would be very much appreciated. Okay, thank you. All right, so it is now 2 p.m. We hope more is on the way, but I'm guessing we will need to start soon. soon. So okay, so let's get started. Thank you everyone for coming in early. Welcome to the Vibration Analysis Journal Bearing Application for Online Monitoring System. Just a few more reminders before we start. Please make sure your microphones are on mute during the talk. If you can open your web cameras, it would be very much appreciated. We will have a question and answer portion later on after the talk, and we encourage everyone to join in on the discussion afterwards. If you have any questions, feel free to write them down the Zoom chat section, and we will refer to it later on. All right. So don't forget to and don't forget to share the link with your colleagues and friends. Okay. So I'm just looking for to stop the music. Okay. So without further ado, I would like to call on our speaker for today. Our speaker for today, Engineer Alan Lisondra. Sir Alan.
Thank you, Pat. Good morning, everyone, and good afternoon.
Good afternoon, Alan.
Should I share my screen now?
Yes, please,
sir.
Alan.
Good afternoon, Mr. Erwin.
Good afternoon, Harold. Good afternoon, everyone. Thank you all for joining on our, I think this is our third installment of our vibration analysis webinar. We're very grateful that you are here ready to learn, and we would like to learn from each other as well. So as mentioned by Patty, that we are turning over the presentation to Alan. But before he go to the meat of the program, we would like to introduce Alan. All right, so Alan, please go to your, all right, Patty.
All right, so introducing Sir, our instructor for today. He is a graduate of mechanical engineering at Rizal Technological University, a licensed mechanical engineer. He is a certified vibration analyst of category 3 in Mobius Institute, Australia, a certified vibration analyst category 2 in Vibration Institute, USA, certified machinery lubrication technical level 1 of International Council of Machinery Lubrication. He is a certified infrared thermographer level 1 of Institute of in Canada. He has 10 years of experience in the field of condition monitoring, focusing on vibration analysis of motors, pumps, fans, gearbox, compressor, and turbine, etc. He is has an experience in balancing and alignment. Currently working in Sabic Hadid, previously condition-based monitoring head at South Luzon Thermal Energy Corporation. So everyone, let's give it up for Engineer Alan A. Lisondra.
Thanks, Pat. Good day to all of you. Can you hear me? It's clear?
Yes, Alan, I can hear you on my end. How about the rest? Can we see a thumbs up
yes,
from our
sir,
participants?
Here.
All right, perfect. Thank you, Jonard. All right. So as you can see, this is a recorded webinar anyway. So if you have some troubles with your internet connectivity, you can do a playback of this webinar on our YouTube channel later on. All right. So Alan.
Okay, so good day to all of you. First of all, I would like to thank Erudite Reliability Services for inviting me to become the speaker of this webinar. And also thanks to everyone for joining us today. We appreciate your attendance and thank you for your interest for this particular subject. Actually, this is my second time already for this particular free webinar. So last time I discussed about the vibration, basic and principle of vibration. So this time I will discuss about vibration analysis and journal bearing application for online monitoring system. So we will only focus more on journal bearing, and we will discuss a little bit of a recap for vibration basics and also a little introduction about the rotor dynamics, since it is related to our subject. So before I start, I would like to share with you a quote for today. So by the way, this is my international certificate. So next, I would like to share with you the quote for today. So the capacity to learn is a gift, the ability to learn is a skill, and the willingness to learn is a choice. So I hope that everyone will learn something today, and I believe that sharing knowledge is very important for us to improve in our daily life. So without further ado, I will start now our training, since this is only a 1-hour training. So if you have a question, I suggest you ask this after the presentation. Anyway, we have also questions after some discussion, and maybe you just put your answer on the box. So first, we start with vibration basics. So what is vibration? So it is a periodic motion of particles of a body to either directions of equilibrium, either forced upon or due to the initial offset from the equilibrium. So vibration is also a back and forth movement of a structure. So, and also it can be a cyclical movement. Also in vibration, we have three characteristics. We have the which is the fundamental, the amplitude, which tells us the severity or the gauge of the severity of our vibration. Second, we have the frequency which tells us the source of vibration. And lastly, we have the phase. So it will tell us the time relationship of between the force and the vibration, or the angular location of the shaft rotation where the highest vibration peak was measured. So now we have also the units of measurement. I believe that some of you already know this, but I will just review. We have displacement, velocity, and acceleration. For displacement, we know that the unit is mils or microns peak to peak, and we use this for stress, motion, so like if you have relative motion or structural motion. Next, we have velocity, inches per second, or mm per second peak, or RMS. So for velocity, if we're interested with the fatigue and energy, we use the velocity. And lastly, we have acceleration for force. In this topic, we will focus more on displacement because we are interested with the relative motion of our shaft. So in the characteristic of our measure vibration, there is a unit for peak to peak, and RMS. So just a review. For example, this is your time waveform. Our peak to peak, I just show the laser. Okay, so our peak to peak is from this point up to this point, and then our peak to peak is from this point to this point, and RMS is the 0.707 of our peak, which is our 70.7%. So we have the time waveform and frequency. So this is the example. Let's just say we have a equipment, we have the motor and gearbox. For our motor and gearbox, we have a fast Fourier transform. On the left side, you see here the complex time waveform. This is a complex time waveform. And for this complex time waveform, it is composed of many frequencies. So let's say this is your frequency for your operating speed, and this one is for the harmonics of your operating speed. The other is for the bearing, the other is for the gearbox. So if you look at on the right side, it is the results from the time waveform that we have. So this is the spectrum, and from the spectrum, you can see here the individual frequency. So it is easy for us to analyze now, since there is a specific frequency that we can see. So in real life waveform, this is how it is. So you have here the complex waveform. Let's say, for example, this complex waveform contains. Out of this, there is 21 hertz, 42, 55, and 78. So for us to segregate this one, we use this FFT spectrum for us to see the separation of those frequencies. So again, this is a review only. So by the way, we have question here. So just put your answer. The best transducer for relative motion. Oh, sorry, Win.
Sorry. Yes. So the question is, the best transducer for relative motion measurement is. So letter A, velocity pickup; B, proximity probe; C, accelerometer; and D, accelerometer double integrated into displacement. Just please type in your answers on the chat. All right. Okay.
Okay.
Keep them coming.
So it's actually part of our participation. At least we know that you are listening, or if you have some information, you can also ask or share with us. Okay, I think that's enough, Win. So here the answer is proximity probe. So as discussed, this is about relative motion. So if we are interested about the relative motion, we will use proximity probe. So now we will go with the rotor dynamics. So again, we will introduce a little bit for rotor dynamics for our information. So what is rotor dynamics? Rotor dynamics is the science of predicting the vibrational behavior of the rotors of any kind. So why rotor dynamics is important to evaluate? It's important to evaluate because we want to know the rotor behavior. Without knowing the rotor behavior, it will create some catastrophic failure, especially in different operating conditions if we don't know what is the behavior of the rotor on those conditions. In rotor dynamics study, there are primary design considerations. First, we have the positions of critical speeds and separation margins. For this one, we will discuss further on the next slide. I will show you some plot for us to see the critical speed and the separation margins. Next, we have the peak response amplitude. So the amplitude sharpness going through the critical speeds. Number 3, we have the steady state response amplitude within operating speed range. So especially if we are already running at operating speed, we should see if it is stable or not. Number 4, the rotor stability under various operating conditions. So stability criteria. And number 5, we have the response to transient event, startup, and shutdown. Okay, so there are terms used in rotor dynamics. First is the natural frequency. So I believe that most of us are familiar with natural frequency because we are almost dealing this, mostly we are dealing this with our machines. So natural frequency is the frequency at which a system oscillates with or without exciting force. There is a term which is related to natural frequency. We have the resonance. It occurs when forcing frequency coincides with the natural frequency of the system. So normally we encounter resonance if we have some vibration with our structure. So there's some coinciding between the forcing, or let's say for example, we have a motor and the structure, those frequency are coinciding with each other. It will amplify the vibration. So next we have the critical speed. So critical speed is a special resonance in rotating machine. So the frequency at which the vibration responds for the forcing frequency is maximum. So what is the difference between the two, the resonance and critical speed? Initially, these two are related to natural frequency. However, their difference is only that resonance is relates to the static part, like if there's some structural resonance, while on the critical speed, we normally use this term as a special resonance in a rotating machine for our rotor. So we want to know the natural frequency of the rotor from low speed to high speed, or from 0 to the operating speed. So next we have damping. Damping is an influence within or upon an oscillatory system that has effect on reducing, restricting, or preventing its oscillation. So in other terms, another definition, you can also say that damping is a dissipation of energy. So it is important for us to know also damping because in this journal bearing, so there's a damping relationship between that. Next, we have the stability. So it is defined as the ability to return back to its equilibrium state when disturbed upon due to initial state or force upon. So as we know in our rotor, rotor or our journal bearings, mostly we have some issue about this called instability. So that's why we have to be familiar also with the word stability. At least we know if our rotor is returning back to its equilibrium state. If not, then it is a term called instability. Okay, so next we have mode shape. Mode shape, it is a general shape or a deflection shape assumed by rotor vibrating at natural frequency. So when you say mode shape, like let's say, for example, this is your first natural frequency or your first bending mode, and this is the second bending mode. This is what the term mode shape is. It's more unrelated on the natural frequency. So let's go more on mode shape. So I believe everyone also, all of us are interested to know what is the relationship between the rigid and flexible, how to identify if our rotor is rigid and flexible. Because in the past, I was in the position, like I want to know which is rigid, which is flexible. So I will just share with you this slide. At least we know what is the difference between the two. Let's say, for example, this is our rotor. In low speed, our rotor is rigid. When we go to critical speed, which is this one, let's say this is a Bode plot. So this is your critical speed. So this is a relationship between your phase and then your amplitude, and this is your speed. So going here, the rotor is rigid. This is the mode shift of that. Passing through, reaching through the first critical speed, it becomes flexible up to here, and then passing through it is flexible because it's flexing. So as you can see here, there's also a relationship between high spot and heavy spot. At rigid, or at this point, the high spot and heavy spot are on the same position or the same location. So that's why if you notice, some people do the balancing first in the low speed, because here, normally the high spot and heavy spot is at the same position. So what you will do, you just put the balancing weight opposite of the high spot. However, passing through the critical speed, there's a different condition. So you have to analyze more, where is the high spot, where is the heavy spot. So going here, this is already flexible as mentioned. And then after that, as we go through the second critical speed, our rotor becomes rigid again. After that, after passing the critical speed, reaching second critical speed and passing through the second, it will become flexible and so on. So here, as you can see, after passing through the high spot, 180 degrees out of phase with heavy spot is already in the out of phase. So that is the relationship of the heavy spot and the high spot sorry. And this example, let's say for example, this is your shaft, this is your heavy spot. So at rigid, you will put here your balancing weight because this is your heavy spot. This is your light spot on the rigid part. However, on this side, it will be different. So we will not discuss it further because this is just an introduction for our information. At least we know how to identify which is rigid and flexible and the relationship between high spot and heavy spot. So as discussed a while ago, this is the example. So as you can see, this is the first critical speed. See, rigid. After nyan, this is the flexible. And then we go again to the second critical speed. Become rigid, and then passing through, reaching through, sorry, flexible, then after that flexible, and then here, so on and so forth. So in rotor dynamics, I discussed a while ago the primary consideration, which is the separation margin. So let's say this is your critical speed. This is your first, and this is your second. So here we have the separation margins. As you can see here, this is the separation margins. So at this part, the rotor should be operating in good condition or in low vibration. That's why if you are working in a power plant or in turbines, there is what we call the soaking speed. The soaking speed also is related to this part, because there's a separation margin. You have to run the equipment at low vibration or in good condition. After we go to the next second critical speed and then to the operating speed. So this is the relationship between them. So I have here, I have here a video. So I will just show you. I will not discuss more here, but I will just show you what is happening with the first critical. By the way, this video is available in YouTube, so you can also see it there. So this is what happening. So let's say this is your first rigid, now it is your second critical. So as we know, there are in equipment like a rotor and generator, and even in the turbine generator, even in turbine, we have like HP, IP, LP. There are different critical speeds. So as you can see, sometimes the critical speed here is low, here high. So there's some differences. So each part, when they reach this critical speed, the vibration will amplify. So as you can see here, our generator don't have critical speed yet here, but our turbine side is already in the critical speed. So after passing through here, as you can see, the turbine is already on the smooth part. Now we are in generator. So now this part generator is passing through its critical speed. Okay. So now we have again question Will.
Yes, thank you, Alan. So the next equation of the following best describes resonance. So you have A, when there is a difference between the geometric and mass center of the rotor. B, condition that results in the amplification of machine vibration when the forcing frequency is close to our natural frequency. Letter C occurs only theoretically and not on operating machinery. Or letter D, caused by loss of lubrication in the plane journal bearing. Yung pinakamahaba ba lagi ang tamang sagot, Alan, pagdating sa mga gantong tanong?
Possible.
Mukhang para-pareho sagot nila eh. Okay, let's give it 10 more seconds.
Okay.
All right, keep them coming. So most of the answers here I see are the same. 5, 4, 3, 2. Okay. Alan?
Good, thank you. So the correct answer is letter B. So resonance, as described a while ago in our discussion, is a condition that results in the amplification of machine vibration when the forcing frequency is close to or at natural frequency. Okay, so now we will discuss about the bearing type. So there are two major bearing type. We have the anti-friction bearing, which is the roller bearing, and the ball bearings. The second one is the fluid bearing or the journal bearing, which is our topic for today. So we will not discuss on roller or ball bearings because we will focus on the journal bearing. So journal bearing analysis. So over the years, as we know, the design of the journal bearing has evolved. And because we have this problem we call instability, is very common. So that's why they're evolving the design for us to avoid this phenomena. So journal bearing are used in a wide variety of rotating machinery such as turbine, generators, boiler feed pump, compressors, etc. So these machines are critical to the plant's operation. So therefore, detecting such rubs, instabilities, unbalance, and misalignment are very important. So as mentioned a while ago, these are the designs which is evolved. So which is included. We have the plain journal bearing, 2 or 4 axial groove, elliptical lemon bore, 3 to 4 loop, pressure dam, and tilting pad bearings. So for high speed, normally they use this tilting pad because this in the high speed equipment like compressors, instability is very common. So they use this tilting pad to avoid this phenomena. So tilting pad means like they're tilting this the oil wedge to prevent or avoid this instability issue, the oil wear and the oil wedge. So as you can see, there's some space. So our main topic is here for the fluid bearing. Let's say this is our bearing. This is here. This is our bearing. This is our shaft. So let's say this is the load. It is rotating clockwise. So here you have your oil wedge, or this is the minimum clearance, the oil wedge. So pressure profile, and this is your displacement. So it's moving like this. So I will show you later. There's also a video for us to see what is the movement of our rotor inside the bearing. So here, unlike anti-friction type ball and roller element bearings, which have a finite lifespan, Bobbitt fluid bearing can last significantly longer when under heavy loading. So we have here example. We have radial tilt pad bearings, and we have radial sleeve bearing. And here we also have example of a plain journal bearing. So here you notice this is where the pressure, the oil is coming. So like if you have a jacking oil pump, here the jacking oil pressure will come here to lift your rotor. So now we will discuss about proximity probe. So since we are using journal bearing, the applicable probe that we have to use here is proximity or the non-contact eddy current probes. It measures the displacement or the distance between the tip of the probe and the shaft. So measure the movement of the shaft within the bearing. So since we're interested about the movement of our shaft inside and between the relative to the shaft, so proximity probe is applicable. So the measure is mils or micron peak to peak. So the sensitivity of this probe is 200 millivolts or 8 millivolts per microns. So this is example. So here our probe, this is our shaft, this is our shaft, the bearing. So here we use this eddy current for us to measure the displacement between the tip and the probe. So in proximity, there is a convention in how we install it. Like here, we have the Y probe on the right side, left side, sorry. We have X probe on the left side. So orthogonally, 90 degrees apart. So common is 45 left top here, and 45 degrees top, right top, X, this one. So it depends on the requirement of the design. So, but if you study or you read about the API 670, in API 670, they mentioned that the installation or the installation of the probe of proximity normally is X is right, Y is left, regardless of the direction of the shaft rotation. So here we have probe cannot be mounted easily in desired 90 degrees. So out of phase, horizontal and vertical orientation probes often have 45 degrees deviation. So this is example of the convention. Like here you have X, Y. So this is the example. So here you notice there is another probe. This is the key phaser probe, which is important for us to see the reference. Like if you have orbit, there's a bright point. That would be the reference for our key phaser. And also we have for our identification of the rotation of the shaft. So now we go with the online monitoring system for diagnosing faults. So there are many available in the market today for our online monitoring for diagnosing faults of the critical equipment. So example of this, we have the System 1 of Benton, Nevada, which is now GE, Setpoint CMS, CSI 2600. So we also have this, the old one, which is ADRE 208 and 408, etc. So again, there's many available in the market. So you can choose which is you like, and just make sure that all the application that you want and interpret will be there. So here, this is an example of what you see on the online monitoring system. You have here the amplitude, you have here the orbit, this is the trend. So this is your data. So why is it important to have online vibration monitoring? So number one, for condition faults and analysis. So because we want to assess the oil whirl, the non-synchronous motions, synchronous phenomena such as mass unbalance and misalignment. The second one is to monitor the equipment vibration, behavior, and shaft position inside the bearing. So we have to identify also the critical speed. So as discussed in the rotor dynamics, I show you about this critical speed. It's important for us to identify it, for us to know which part we should avoid. Number four, the response to transient events, startup and shutdown, and stability under various operation conditions. And number five, historical data of vibration plots. So it will also save time because we will not stop the equipment for us to get again data. So others improve equipment reliability and availability as well as decrease maintenance and operation cost. So since the data is already there, you don't have to stop the machine for you to get those information. So if you stop it, it will cost high in operation and maintenance. So it is good to have in our plant. So now we go with precision. So precision is defined by the direction of vibration motion and direction of the rotation. So as you can see here, this is the example of our what we call forward and reverse. Forward means you are on the, this is, let's say this is the rotation, this is counterclockwise. So this is your bright spot, this is your blank. So you're from bright going here, this is the same here. You're on the rotation. If you're on the rotation, that is forward. Forward. This one is reverse, meaning here, this is the clockwise, you are going reverse. This one. Sorry, this one. So reverse, this is clockwise, this one is counter, this is clockwise, this is counterclockwise. So this is reverse, against the direction. So now we have spectrum plot. So spectrum plot also is a plot between frequency and amplitude. So FFT is performed to the time waveform to convert the frequency domain. So we have a half spectrum and full spectrum. So normally you see this half spectrum if you're analyzing your rolling element bearing. So this is the common spectrum that we are using. So it is obtained by FFT of time waveform of the signal. Next, we have the full spectrum. So full spectrum is obtained by FFT or orthogonal pair of probes. It is also called as a spectrum orbit. So if you can see here in the full spectrum, you have zero positive side, zero negative. So 0 to positive, meaning this is a reading of your X and your Y. So this is a combination of the two probes. This one is only one. So this is example of our probe, our spectrum, sorry, and full spectrum. This is spectrum, full spectrum, full spectrum. So here I have question. So which is forward and reverse in the spectrum plot? Does anybody know which is the reverse and forward? So just pick A, B, C. Let's say you have forward. Is it A, is it B, or maybe to answer? I will. Yes.
Hi, Alan. So I can see some responses coming in on our chat. So maybe for the other participants, medyo sa tingin niyo medyo advanced na to for you. I suggest na you check our YouTube channel, whereby Alan shared the fundamentals of machinery vibration analysis. And also, if you have a training opportunity for next year, we invite you to our training on the full training on vibration analysis for 5 days. So, okay, thank you for the responses I see on the chat. I see letters A, C, B, B. Okay. So, medyo iba-iba ang sagot nila, Alan.
Mm-hmm.
All right.
Yes. So again, as mentioned by Win,
go ahead, Alan.
Yes. So again, as mentioned by Win, this is a little bit advanced. So kasi yung gusto namin mangyari dito is for us to share the knowledge about this journal bearing. So in journal bearing, normally we have to go a little bit advanced in the topic for us to know what are the plots that we are seeing in this type of bearings. Of course, we're dealing with the turbine, compressors, and critical pumps.
Right. So let's give it 10 seconds for the rest to respond. So 10, 9, 8, 7, 5, 4, 3, 2, and 1. All right, Alan, what is the right answer on your question?
Okay, the right answer is, this is A is forward, B is reverse. So actually, letter C is also forward. So A and C is forward because this one is always on the positive side, C. But if you want to compare this A and B, forward is A, reverse is B. Why? Your reference should be this, let's say this is 0. From 0 to positive, your peak here, or your peak on your your operating speed is higher than your negative. So if positive is higher than negative, it is considered as forward. On this side, this reverse because your part here is lower than your negative. So negative side is higher than positive side. So that's why it is reverse precession. This is the example only of the forward and reverse. So maybe somebody will ask, what is the importance of forward and reverse? So we will discuss that on the later part, since we will also discuss about rubbing. So, and oil wear, oil whip. So if you have a reverse, mostly it is indication that you have some rubbing, but not all the time. So that's why you have to look at every plots or every data that you have on your system. Or it could be also like what you call this, the switching of your X and Y. Maybe you install the X on the left and the Y on the right. So this is also a good indication for you to see. Next, we have the waterfall diagram. So waterfall diagram is a three-dimensional plot of spectra at various machine speeds, sometimes called a spectral map. So as you can see here is a full spectrum example of the waterfall diagram. You have here the plots, spectrum plots for the positive. We have here the speed. And this is, this is the time from your startup, and then this is your speed from 0 up to what speed you, let's say from 0 to 3,600. So next we have orbital analysis. So orbital analysis is called the Lissajous pattern, so represents an instantaneous position of the rotor within the bearing of the instantaneous position of the bearing pedestal. So it provides an indication of the dynamic movement of the center of the shaft. So this is your probe, that's your Y and X. So this is your orbit. So from time waveform, yeah, you have the orbit. This is the orbit. This here, this clockwise, counterclockwise. This is your bright blank. This is rotating at clockwise. Sorry, counterclockwise. So what is orbit? So we are interested in how shaft is moving inside the fluid film bearing. So it will tell us vibration of motion of the shaft. So it will indicate oil fluid instabilities, unbalance, misalignment, rubs, loose parts, and shaft cracks. So we have here questions. So what do you think is the normal shape of the orbit, and why do you say so? So for this one, maybe you can just answer the first part. Like, what is the normal shape? Because if they will explain, it will be long.
Okay,
Is it
so
circle?
among our,
Is
is it circle? Is it what, crooked, orthogonal? May mga options?
Yes, parang mga ganun.
So anyone who would like to answer?
May idea.
Right, Ralph,
So
did you
give
turn on your
them.
mic? All right, Jonard says oblong. Okay.
Okay.
Bjorn said
Circle.
circle. Okay. Lahat na ba ng shapes? Okay.
Yes, so
Oval,
at least
sabi ni Ralph.
know what is
Oval.
the normal shape of the orbit.
Elliptical. Michael said elliptical.
Okay.
Okay. All right. I guess in the interest of time, Mahish Bin also said elliptical. Yeah, so let's hear from Alan.
Okay, so the answer is this one. So the answer is the dynamic of the shaft is a function of mass, stiffness, and damping. So clearly, the mass is greater in vertical direction. So and stiffness of the system is not equal in vertical and horizontal direction. So if you notice, normally the stiffness is always greater than on the vertical side. So that's why. Therefore, it is perfectly normal for orbit to have elliptical shape. So this is the answer. So by parang ideal natin, gusto talaga natin circle. But in actual, it is not because of this condition. Okay, next. Pwede ka ba ma-play to win?
Yes,
Skip ko na lang.
you should.
Sige.
Yep, sige, play mo.
So this
Alright,
is the
we can see
example.
it.
Again, this is available in YouTube. So I just want to show you how the orbit or the shaft is moving inside and how to see the orbit. So this is your bearing, this is your probe, proximity probe. So as you can see here, you have this orbit. So this is how it is moving inside. And while it's moving inside, you see the orbit. So if it's go to the right side, this one. So I will not show you more of this video. I just want to show you what is happening inside and how to see this orbit. So in orbit, there's what we call direct and filtered. So what is the difference between the direct and filtered? So sa pinag-aralan natin, ang direct, it is the overall vibration. So ibig sabihin, it is a combination of all the frequency. If you see the filtered, let's say filtered 1x, you're interested only in 1x. So you want to see the 1x, it is filtered. You have to use the filtered one. So this one also, direct, is a combination of 1x, 2x, maybe 3x. So, and then there's a filtered 1x. So let's say, for example, you have a misalignment issue. So if you want to see if there's a misalignment, you go to this 2x, and then you will see H shape. So something like that. So next we have unbalance. These are the examples of orbit problem. So we have unbalance. So unbalance is the size here. The size of the orbit will increase. However, it will retain the elliptical shape. So alam naman natin yung balance pag merong mass, the mass distribution is not equal on the rotor, or there is a shape of our center. So here you can see it is already elliptical. As we discussed, elliptical is a normal shape. However, if the size of that elliptical is high, like the amplitude is high, it is also not good. So that is an indication that you have unbalance. So this is the example. If you filtered that orbit, you will have like this. So this is the rotation, bright and blank. So see, it's forward precision. This one is forward precision also. So here I just put here the scale because this one is on the micron, so you just have to multiply by 25. So, but anyway, we're only interested in the shape. Don't find in these values. So what I want to show to you is what is the shape of the unbalance. So this is the unbalance with the time waveform. Let's say this is clockwise. This is your orbit. This is your time waveform. So this is the relationship between the two. Next, we have misalignment. So misalignment, so it is also like an orbit, but it's a little bit like shift, squeeze. Kasi meron siyang preloaded. Pag preloaded ka, medyo naiipit. So misalignment cause an orbit shape of kidney shape. So this one. So pag lumalala yung misalignment, yan, medyo lumala ng konti pala, this is nagiging kidney shape. After that, H shape. H shape results from a badly aligned machine with preload bearing in the direction of the perpendicular to the path of the orbit. So this is the example of misalignment, if it's badly misaligned. But of course, you have to take note about the amplitude also, because first, if it's very low but it's showing some misalignment, maybe it's still within the acceptable limit. Because in alignment, we also have these limits. But going through your system, you will become more familiar of what is happening. Like you have a trend, so you know if it's increasing or not. So here example of preloaded due to misalignment. So this is like this is direct orbit, and this is the filtered orbit in one time or 1x. So this is the orbit with time base. This is the time waveform of your orbit. So next we have ROBS. So ROBS, so orbit analysis is a good tool to identify ROBS. So we have what is called partial or complete ROBS. So from 8 to full circle to something. Pag ROBS kasi, mapapansin nyo, although 8 siya, marami siyang dots. There are many dots you can see in ROBS. So sometimes it is reverse. Like for example, this one. So you can see here, this is one part is clockwise, this is clockwise, this one is clockwise also, but this one is counter. So there's some part is rubbing. So I will play. So this is what happening in your rub, like that. So again, this is available in YouTube. If you want to see it, you can go to the YouTube also for reference. So here we have Rotor Rubs guidelines. Let's say we have the full spectrum plot. This is your full spectrum. So this is the normal. So as discussed a while ago, in normal, your positive is high. Your peak is high, your negative is low. Here also. So typical rub plot, you can see this one is high, a negative side, and your positive side is low. But again, it is not always true. So you have to also to check other plots like your shaft center line, your orbit, and everything. So here we have the example of the orbit plot. This one is your normal, like this clockwise from your dot going here. This is also clockwise. So this is normal. So orbit is flattened, heavily preload. So this is, if there's some rub, you can see there's a lot of dots. And unti-unti siyang naghihiwalay. In Tagalog, naghihiwalay siya. Pag unti-unti naghihiwalay, ibig sabihin lumalala. So it becomes more heavier. The rubs becomes heavier if the dots is spreading. So I have here example. This is example of rub with multiple orbits. As you can see here, from part na makapal siya, unti-unti siyang naghihiwalay. Pag naghihiwalay na siya, nagiging ganito. So parang mas lumalala yung rami. So this is example of our rubs. So this is the time waveform you can see in your rubs. Here is the normal, like sinusoidal or harmonic. Here you have some truncated. But again, there are many reasons of truncated waveform. It's only one. So later on, if you study about rotor dynamics and more on in-depth in journal bearing analysis, you will understand it more. So now we have what we call fractional frequency. So fractional frequency is a whirl frequency is often a fraction of less than 1, so of the rotor speed. So we have forward whirl. It is a whirling motion in the same direction as rotation. So that's why it's forward. So it is encountered in the oil whirl, oil whip, so whirl caused by fluid trap in the rotor. So maybe if you're familiar with steam whirl, it's also part of this. So here we have the orbit of 1/4 x. So you can see this internal loop. Difference of forward and backward is that the forward is internal loop. So you can see inside. The loop is inside. This is your dot. This is rotating clockwise. This is counterclockwise. Sorry, this is counterclockwise. This is counterclockwise. The other one is whirl frequency less than 1/2. So this is also loop inside. So this is the peak, highest peak. The other one is, sorry, I will discuss also more with oil whirl and oil whip. So if you see oil whirl, the tracking operating speed is at 0.35x to 0.47 or 35% to 47% of the vibration amplitude as sometimes severe. So if the frequency becomes equal to natural frequency, at this point, yun yung tinatawag natin na instability known as oil whip. So if that frequency will coincide or at first natural frequency, it will become equal. Sorry. So if you're working power plant, there's what we call the steam loading in operation side. So unloading the rotor from an equal conditions of steam admission can cause change in the bearing stiffness and damping. So that's changing the critical speeds and induce oil wear or oil whip instabilities. That's why it's very important at the beginning that the steam loading is properly done based on the procedure and the requirement. Because sometimes you will notice why the vibration becomes different from the last startup that we have. So you have to see all those parameters. That's why in vibration analysis of journal bearing, it is also related on how we know the operation and how we know the behavior of the equipment, the history. and the operating parameters for us to relate everything. So next we have the backward whirl. So caused by the drive friction rub between rotating and stator parts less frequently. So it normally happen not less frequently only. So the example of this one, you can see this is external loop. So external. The forward is internal loop, backward whirl is external. So if you have some like major rubbing, this is what is happening on your machine, on your orbit. So see, this is external. So orbit rubs backward whirls 1x and 1/4 x vibration. So next we have the shaft center line. So shaft center line is a position location of the rotor shaft center line inside the bearing. So it is a plot of equilibrium position of the vibration shaft center line inside the bearing. So this, just don't mind this circle. Actually, this circle should be higher. Like this indicates the clearance of the bearing, like your bearing. But this one, it's not properly set. So just ignore this one. Just go with this part. So as you can see, this is the shaft center line from 0 to 3,600 RPM. This one 0 to 3,600. This is the behavior of your shaft when your speed is increasing. So normally, like the shaft, ideally it should be like going here. So if you have like tilted pad bearing, normally it's like from here to here, almost in the center. But since this one is example of a journal bearing, the journal bearings, again, it is like, what is it, prone to like instability. And then there's some machine characteristic which is related to our topic, like there's a mass, stiffness, and damping. So there's a difference between those designs. That's why you see this differently on like in tilting pad. So again, you have to monitor this shaft center line every time you have a startup or your shutdown for you to see what is the condition of your equipment, if it's changing or not. So as you can see here, the other side is going on the right side. This one is on the left side. So maybe this is on the bearing 1, this is on the bearing 2. So what's happening? So you have to know maybe the load on the bearing number 2 is different from the load on the bearing on number 1. Loading, I mean in the loading on the bearing. So maybe there's also a swapping between X and Y. That's why your bearing number 2 is going here. The rotation is like this, clockwise, counterclockwise, and then this one is counterclockwise. Counterclockwise, this one is clockwise. So maybe there's some swapping. That's why the other bearing have different shaft center line. So those are just some indication also. So that's why during the less speed, like if you're in the just doing your turning gear, you have to see also those indications. So we have your example of rubbing, indicating rubbing. So this is a shaft center line. So as you notice, the graph is like chaos. So meaning paiba-iba siya. So parang kung sa Tagalog, bumabanda-banda ba. So kaya nakikita niyo, nag-iiba-iba yung location ng ating shaft center line, yung mga dot. Napansin niyo dito. So this is one example of shaft rubbing when you look at your shaft center line. So this data is during the shutdown or cost down. So orbit and shaft center line. So center line moves higher. So orbit shows force from the side. So moves more vertically than horizontally. So typical on inboard bearings when misalignment is present. So this is your example again. You have your direct, your filtered 1x, and this is your shaft center line. So if you have some misalignment, it looks like some kidney shape. And then if you look at your 1x, it's a little bit preloaded. So this is the shaft center line. So next, we have resonance and critical speed. So we discussed earlier about these two. Sorry, I just go a little bit. So occurs at frequency and speed that are governed by natural frequencies, damping and vibratory forces. So again, this is your critical speed, right? So as we go to the first critical speed, you have a phase change of 90 after passing that you have 180. So this is your amplitude, this is your phase. So this is some example of mode. This is second bending mode or second mode or second critical. So resonance occurs when the forcing frequency coincides with natural frequency. So what is important why I'm discussing this? Because the next plot that I'm going to show to you is Bode plot and polar plot, where we are going to see this phenomenon, resonance or the critical speed. So high amplitudes of vibration will be present when the system is in resonance. So again, all the plots that we are seeing are actually on the system that we gathered from our proximity on the journal bearing. So these are all the data that you will see and analyze. So next we have Bode plot. So a graph of amplitude versus speed and phase versus speed. So it is useful for observing the vibration in transient. So transient like startup or cost down, and startup, cost up, shutdown, cost down. So it is useful in identification of critical speed. So let's say it is cost down data. So from this operating, it goes down here. This one is your first critical. To know if it's critical, there should be a change in phase. If it's just straight, the phase is not changing, even though your amplitude is increasing, it is not a critical speed. Maybe something is wrong with the equipment. So other problems. Also this one. So this is a sample of plot from like a system here. This is the phase not changing. This is vibration. Once it go up here, there's some phase change. So it's clearly the first critical speed. So I go here like this. So this one is your first critical speed. It's around 2,800. So maybe it is the second, we don't know. So again, our manufacturer is also giving us the specifications of our rotor. So before we start doing this, or be familiarized first with your specifications given by your manufacturer, because in the first stage, like during the commissioning, this test was also conducted. So you have to see the data that is on your documents based from the manufacturer design. So polar plot, so a graph of amplitude versus phase for various machine speeds. So contains same information as Bode plot, but represented in polar coordinates. So this is example of polar plot. So from here we have 0, then the speed is increasing. So here you have the highest, there is a phase change. As you can see, this is 0 degrees from here. This is 90, so there is a change of 90 degrees. So this is your first your critical speed, and then after passing that phase, change to 180. So in actual data, you have here from 0 to 3,600. So here, there is a phase change. This is your first critical. And then this one is the last. This is your operating speed. So this is your first critical on this part. So just show. So it's around 2,800 or 27. So if you compare it with Bode plot, again, these are the same information. This is the same, around 2,800 also. And on your polar plot, it is also around 2,000. So mostly those two will show you those data. Just to confirm, you have to confirm between Bode plot and polar plot. By the way, these data are the same. From same reference. This one and the other one on the Bode plot. Okay, so now we have question. Will?
Yes, actually, we do have some questions on the chat. Would you like to go through those first, or you want to do it later?
Maybe later.
Okay, so on this question, in the interest of time, at what condition is best to check critical speed, natural frequency of a rotor during startup or shutdown, and why? So Alan, let's just go because it's 3 o'clock on my time already.
Yes. Okay, so I'll just go.
Yes, let's just go over this.
Okay, so the answer for this one is Natural frequency can be measured during startup and cost down. So startup and shutdown. So to obtain the critical speeds. However, values of natural frequencies obtained during startup may be variable because of the acceleration and loads imposed in the rotor. So for this reason, cost down tests provide the best data. So in addition, some machines or like turbines, for instance, do not achieve thermal stability during startup. So this is the main answer for best to check the critical speed. So if you want to check the best critical speed, it should be in the cost down or shutdown. So these are some examples of faults for compressors. So this is just additional info. Actually, we're almost done with. So let's say for a fault, excessive clearance. Here, I think there is some question a while ago. I saw what is the possible cause of shaft rubbing. So maybe this one is the answer. Like if you have some rubbing, excessive bearing clearance, first of all, high 1x vibration with rotors cannot be balanced, may go to unstable and change critical speed. Bent or bowed rotor, 1x high vibration drop at discrete speed, the phase change mass unbalance. So the main indication of bow is like if you're doing the cost down data, if the amplitude on the critical speed, instead of going up, going down. So you have data before and then you compare it before the critical speed, the vibration is going down. So it is an indication of bowed rotor. Build up of product deposit, so one time and or rub, so rotor or casing. So shafts misalignment, we have high 2 times in one direction with 1 time on action. We have unbalanced rotor, high 1x or 1 time operating speed and fixed phase angle, and we have oil whirl, oil whip, excessive vibration, subsynchronous frequency, and we have operating in surge range, pressure impact on the rotor rings of natural frequency. So these are the example for compressor fault analysis. There are many fault analysis for compressor. I just pick out the major one, which at least we will be familiarized. So again, another one, if you're turbines like out of balance, steady 1x, condition of occurrence, this one, so suggestion, remedy like rebalance, fill marks. So I will not read this all, just for our information. Maybe you can do some screenshot if you want. So I think we're almost done, Win. So
yeah,
again,
but before we go, Alan, there are some few questions. There was a first question that asked, please tell me how to set the clearance circle in system 1, and we are 408, ADRE 408. Mahishvin.
Can you repeat again the question?
Please tell me how to set the clearance circle in system 1, and we are 408.
Okay. So you are saying about the clearance, the in the shaft center line. Do you mean?
Can you hear me? This is Mahilvin.
Yes, I can hear you.
Sorry, that's my question is, I just want to know how to set the clearance circle in system 1 and also in ADRE 408 software, ADRE XP,
Okay.
SXP. Yes,
Yeah.
I know the clearance, I know the bearing clearance. So just I want to know how to set, especially in ADRE 408, ADRE SXP software.
Okay. With regards to the setting of your system, like 408, system 1 or CMS, actually we are not on this on the stage that we can see how we cannot teach you how to do it because it's part of the manufacturer. So you have, maybe it's better for you to ask the vendor of how to use this one, because there's some system that I'm not familiar. Like for example, me, I'm using Setpoint CMS. So 408, I just use it a little bit, but not too much. So first, you need to know the clearance between your shaft and then if you're bearing this one. So this is the clearance between the two. You have just to put that one. Maybe you can ask your vendor or the manufacturer on how to set that part.
And thank you very much. And one more question, maybe it is a very basic question, but I want to know that where the XY probes are mounted inside the bearing housing, or it should be mounted outside the bearing housing?
You mean the
The
proximity?
proximity
Yeah.
probes.
I already showed you in the previous slides regarding the proximity should be inside the bearing. So
Inside,
if you know,
that means it is it means it is drilled and it is going inside the bearing housing. No.
yes, it is going inside because you are reading the shaft vibration. So without that information, you have to this in instrumentation they set that as negative 10 volts, minus 10 volts. So in every difference between the shaft and your tip of your probe, there is a certain volts. So it is
Okay.
inside.
Right. So the probe is mounted inside the bearing housing.